So the basic interest of changing the plastic material is actually the waste issue.
Right now, we're living through a major era in our history, and it's one that will impact us for centuries to come. It's called the plastic age, and it's impossible to picture our world without this remarkable material.
We have pollution taking place in the ocean, and to date, something like 140 million tons of plastics swimming in the sea.
How can the development of bioplastics help reduce waste and even provide solutions in other areas? In this episode, we'll explore the world of bioplastics, what they are, how they're used, and the impact they could have on our plastic-reliant world.
I'm Dana Clemenson.
And I'm Micah Schweitzer. This is Balancing the Future from METTLER TOLEDO.
On this show, we delve into the world of science and technology and explore its transformative impact on our lives.
Let's jump in.
In the middle of the 20th century, the plastic industry boomed, powered by cheap and abundant oil. But that changed in the 1970s.
The oil crisis, when producers in the Middle East turned off the taps, sent oil prices soaring.
This scarcity sparked fresh interest in researching alternative materials that could replace petroleum-based plastic.
But by the mid-1980s, new oil fields reignited our love affair with petroleum, and traditional plastics reclaimed the spotlight.
Fast forward to today, and plastic still rules the world. So before we move forward, let's answer one key question. What is traditional plastic?
So plastics, well, that's actually a polymeric material. So we have bricks that are aligned up after each other. So it's a monomer-based construction. So there are many different versions of polymers that you can find also in nature, branched one, block ones, and so on. And the bioplastic ones are actually quite similar to the plastic ones.
That's the voice of Manfred Zinn, professor at the Institute of Life Sciences at the University of Applied Sciences and Arts in Sion, Switzerland. He spoke with Micah.
But most of the plastics that we've been using for the past half century or so are not bioplastics, they are petroleum-based plastics.
That's perfectly true, yes. So actually, first polymers were described in 1927, and then kind of a special plastic started that was complex bakelite. So it was not really a true polymer, more cross-linked material. And then the whole plastic industry took off in the 1950s, 55s. And from there on, it was really a true exponential growth until to date, where we have a production of 450 million tons of plastics per year.
450 million tons.
Yes, it's a huge number. Incredible.
Interestingly, Manfred began working on his PhD during the oil crisis. This ignited his career-long fascination with the science of bioplastics.
I mean, do you have a frame of reference for that? What would weigh 450 million tons?
Oh, my goodness. So it's a very, very big number, difficult to explain. I think it's almost food that we consume in Europe, I would say, yeah.
The equivalent of a year's food consumption for an entire continent?
Yeah.
Okay. We wanted to get a sense of where you are today. Where are we talking to you?
Okay, I'm located at the Institute of Life Science here in Sion. Above me, we have the labs, and below we have the pilot plant. So we are in a good position so we can directly interact and see how things are running. So it's a great place to work, and I enjoy it very much, yeah.
And what room are you in right now?
Right now I'm in the creative space. So this is our room where we have our meeting seminars, where we come up with crazy ideas, and it's a lot of fun to be here, yeah.
Well, here's to many more crazy ideas.
Yeah.
Now, when you say that plastic production really took off in the 50s and 60s, plastic production then was focused more on plastic as a durable product, I believe, and not single-use so much.
Yes. So that on one side, it's really the beauty of the plastics. You can shape it, you can form it, you can use special stains or colorants that you can add as an additive. You can render stiff polymer more flexible. And because of the price, so the plastic production at that time was further decreasing because of the increase of the volume. So the tendency to use big amounts of plastics just for packaging and single-use or short-term use material took off. And that's now the problem that we are actually facing nowadays, so the microplastics.
Is bioplastics a response to the increase in plastic production or a response to the increase in single-use plastics?
So maybe we need to look what are actually bioplastics. So the definition of a bioplastic is that it is bio-based or biodegradable or both, actually. That's a little bit a problem that we have. So if you are seeing a biopolyethylene, that means its source is actually coming from biological origin. So for instance, from ethanol. And however, degradability is not given. So when I'm talking of my polymers that I'm producing, I try to go to a different term or use a different term like biopolymer. And then things are more clear that this is a biosynthesized polymer that is also biodegradable.
So what I hear you saying is that you need to compartmentalize what we might call bioplastics into two areas. One is it simply made out of biomaterials? And the second is it made out of biomaterials and can it be biodegraded or recycled?
Yes. Actually, there's also a third species. So there are also medical polymers that are petrol-based, but biocompatible and biodegradable. But they are really in small amounts produced.
These are like for medical implants?
Yeah, drug delivery systems and implants, yes.
So what is the basic problem that you're trying to resolve with bioplastics?
Okay, so the basic interest of changing the plastic material is actually the waste issue. So if we want to solve this issue in the future, we need to attack this problem at several levels. So first of all, we would need to find resources that are replacing the petrol resources. So if we especially think of the end-of-life utilization, so nowadays many plastics end up in incineration plants. So we produce then CO2, so that's a major issue. Now we have pollution taking place in the ocean, and to date something like 140 million tons of plastics swimming in the sea. So it's a huge amount. The problem is also the materials don't stay at they were shaped, so they fragmentize, meaning they are ending up in microplastics and eventually also as a kind of a nanoplastic material.
Which enters the food chain and ultimately can even re-enter the human body.
Yeah, that's actually a very, very big concern that we are, through the food chain, also taking up plastics in a daily manner, actually.
Microplastics make their way into the food chain in various ways. Direct consumption is one of the most well-researched pathways.
Studies have shown that they're present in many foods and drinks, including salt, seafood, sugar, and beer.
What's less well known is that microplastics can also be inhaled. A team from the University of Plymouth concluded that we potentially take in more microplastics from airborne fibers than from the foods we eat.
It's perhaps no surprise, then, that in 2022, they were detected in human blood.
And while we don't yet fully understand all the effects of microplastics on the human body, recent research suggests they may increase the risk of heart attacks, strokes, and other complications.
This is why researchers are developing bioplastics that can more easily break down in the environment. But that brings up questions about their durability.
So another important aspect is certainly the degradability in the environment. So for sure we want to have materials recycled, and that's a big challenge also for the biodegradable ones, that one shouldn't, compost it, you can compost it, but then you need to make sure that you get the methane back in order to have at least the energy that is contained in the polymer. But I'm actually favoring recycling of the bioplastics in such a way that we can profit from the material itself, so building up new materials. And this will also help to decrease the cost of these expensive bioplastics.
It would seem that one needs to think about both the creation of, or the production of the plastic, the bioplastic, and then, as you're saying, what happens at its end-of-life stage. If you create bioplastics, for instance, ethanol-based bioplastics, and we forget about the end-of-life stage, can they also contribute to, say, ocean pollution or microplastics?
Well, for sure. So if they are not biodegradable, so then we have actually also an increase of the problem. Huh? So we should really make sure that we can control the loops. So recycling is really enhanced, and unfortunately not all plastics can be recycled. So it's polystyrene, it's quite impossible to recycle.
And plastic recycling overall worldwide has been decreasing.
Right. So that's another alarming system or situation, I would say, that recycling systems are getting also expensive in comparison to recycled materials. So, for instance, PET material, polyethylene terephthalic acid material based, so the PET bottles. So the recycled PET material is right now more expensive on the market than the pristine one, the petrol-based one. So the market is actually also evaluating what plastics are cheaper, and from time to time argumentations like public relations also are helping to use or promote actually these recycled materials.
So it sounds to me, Manfred, like you're dealing with scientific issues on the one hand, but also economic issues on the other.
For sure, yes. So in my research group, we are looking at also new materials that can be produced using bacteria. So we are keeping bacteria quite happy, so we feed them all good stuff. That means good carbon source like fatty acids, oils. So we are also using waste oils.
You mean like French fry oil?
Yes, for instance, yeah.
To feed the bacteria?
Yes. And what they do under specific growth conditions, they accumulate internal carbon storage compound, which is called polyhydroxyalkanoate. And that's nothing really special. So that's a large part of microorganisms in nature have this capacity to intracellularly store this polyester, and this polyester we can later on extract out of the biomass and then also process it like a regular plastic material. I have also here a sample of biodegradable material, so this polyhydroxyalkanoate, and this is fully 3D printed.
So you're holding up a product here? So this looks like it's almost like a 3D web.
Yeah, it's actually representing kind of a membrane protein that is helping to exchange materials from inside to outside in a cell. So it's just an art model, but it nicely shows that you can process it in such a way.
And that was 3D printed?
Yes. So we don't need to have a kind of a mold, so we can use free parts, and this will also reduce the production costs of such a material, because in order to economize mold usage, you need to have at least 10,000 pieces produced with the same mold. So they are quite expensive.
Traditionally, plastics are shaped using molds. This allows for the mass production of a single item very quickly. This is partly why we've reached the point where we can produce 450 million tons of plastic, like Manfred mentioned earlier.
However, the downside is that creating complex shapes with multiple parts is much more difficult. That's where 3D printing comes in. For example, a complicated object like a whistle can be created in one piece with the ball already inside.
3D printing is especially useful for small-scale production and specialized designs. But, as you've probably guessed, it isn't very scalable.
As of today, only 0.5% of all plastic produced is a bioplastic. In the future, Manfred hopes that number will rise to 10 or even 20%. However, to make that happen, more applications will need to be explored.
So I see many applications. First of all, most important one is the application in packaging, so short-term applications. Then also the medical side. So the polyhydroxybutyrate that I just mentioned, with this melting temperature, is actually already part of all living species. So we have oligomers in our body that may have a function in diabetes control, but we have also in our membranes channels that are based on this polyhydroxybutyrate. So it's a material that is already biocompatible. So if we eat it, then we don't need to expect something big happening.
Okay, but we're not going to start eating our food packaging. I mean, this is just if it were. So you've touched on the recycling side of this a little bit already. We've talked quite a bit about the production side, but let's close this loop. What are the challenges around biopolymer recycling that you're trying to resolve now?
Okay, so the biopolymers have been polymerized also. So that means there are enzymes or catalysts that help to make the connection between these bricks or monomeric units. And there are also enzymes that are allowing to split such bridges or connections. And depending on the conditions, you can use biosystems that are doing this job, like specialized enzymes, or you can also go for whole biosystems that are doing that. In parallel, there are also chemical steps that allow recycling to the monomeric unit. So there are many options. What I also think is of importance is that we are trying to valorize also the product into different sub-products. And so we have developed also a method in order to convert this polyhydroxybutyrate, this biopolymer, into a green solvent. So it can then also help to isolate again the polymer out of the cells. But in addition, it is also a good green solvent, can be used for medical applications as well. And what we also are looking at is the energy content. So in case there is overproduction of this material, we are also able to use this biocarburant or petrol. Another part of this solvent is also that we could use it again as a substrate in order to produce the same plastic again. So we are quite flexible now with this approach.
Interesting to me that you mentioned creating more plastic out of the plastic as the third thing you said, because again, sort of from a consumer mindset, one thinks of, I recycle my plastic bottle and a new plastic bottle comes back to me. But you're really looking, yes, that's one option, as you say, but you're really looking at other ways of reusing this material.
Yes, fully agree.
At least from a consumer mindset, one thinks a lot about turning plastic into plastic, right?
Yes, that's actually a very reasonable approach for the solvent approach. So that would also give us more flexibility, what we are doing with these materials. So first of all, I mentioned that we can use it as a solvent to extract the polymer out of the cells. But in addition, we have also then the possibility to generate energy for transportation or also for electricity out of these solvents. So what I also wanted to mention is this is really an approach back to the very, very basic unit, and from time to time that's really quite useful. So if you think of, for instance, having mixed materials, and one of them is now this bioplastics, you can selectively choose that only this material is then converted into a solvent. So that should also enable better recycling of mixed plastic streams.
Interesting, because that's a fundamental challenge with recycling right now is mixed plastic streams.
Yes, fully agree.
Will you be able to recycle more in total because you have multiple options for the recycling process?
Well, I'm really convinced that we need to work on recycling options also for biodegradable materials, because the production costs are quite large. So right now we are 2 to 4 times more expensive at a large scale of production. So there are many approaches in order to further reduce the cost of 1 pound or 1 kilogram. However, the advantage of petrol-based plastic is that it's from time to time, depends on the country, subventioned, and in addition, it is also part of fuel production, meaning large volumes are converted and substrates or the basic chemicals needed for the plastic production are kind of a side product. And using this approach also in bioplastic production, so having such kind of biorefineries, we will be able in future to reduce the cost even further. So if we don't have only just one goal, the plastic production, but in addition also kind of fertilizer production using this biomass, or everything should be then interlinked in order to have a really optimized system. And there I see a very, very big potential in future.
Biorefineries combine multiple bioprocesses. They've been around since the late 1990s, and they're gaining momentum now because of the growing demand for alternative fuels like bioethanol.
These facilities not only produce fuel, but also turn byproducts like biomass and syngas, a high-energy gas, into valuable resources.
Pilot projects are up and running on a small scale, supported by initiatives in the EU, Canada, and India. The goal is to have full-scale biorefineries in operation within the next decade.
Once established, these will provide alternative fuels and bio-based products, offering greener alternatives for everyday use. At scale, these could have massive potential.
But to reach that scale, the new possibilities need to be effectively communicated and embraced by the public and the market to shift our relationship with plastic.
I think we already need to start right now. It is communication. So there are issues that are complicated. So I just mentioned also this term bioplastic, meaning it's bio-based but not biodegradable. So that's a little bit unfortunate development that we have to correct. And one solution I mentioned is that we are using the term biopolymer in order to proceed in a more understandable way. And there are also aspects that we need to consider as well in our society. What does it do when you don't put the material back into the proper collection bin? Or what could happen, and so on. These issues that are, well, unfortunately also causing big problems in recycling.
So a lot of education.
Yes.
Is there a future for non-biodegradable bioplastics?
For sure. There are applications when you are thinking of airplanes or very materials that are of high impact resistance, or where you need to have a high-performing material. So windmills, for instance, also there you want to be sure that there is no corrosion taking place due to fungi or whatever. Yeah.
So the biodegradability is a liability in certain applications.
Yes.
Yeah. And then, of course, and then you get into these issues of names and how people understand what a thing is or what it means in terms of what's biodegradable and what's not, or what's recyclable and what's not.
Okay, so this will be a continuous challenge to separate the materials. However, there are also tools now well established, like the Raman spectroscopy or the Fourier transform infrared spectroscopy. These are optic systems that allow identification of the material. But first of all, you need to have pure material, and then the material should have the similar property. So for instance, if you have a plastic case made of polypropylene and you have with a dark material, staining, whatever, and you would like to combine it with a polypropylene that is transparent for a cup and so on, it will be almost impossible to reproduce a cup again which is transparent. So there are quality issues that are, taking an important role.
And we ask all of our guests this, what would your advice be to somebody who wants to get into the field of biopolymers?
It's a huge field, and it's a very interesting field because it's so interdisciplinary. You can work just with computers and design polymers and try to simulate interactions in order to reduce the crystallinity or adapt the system. You can also do pure chemistry, so modification of the side chains, for instance, can also help to covalently bound the antibody part in order to have a medical compound, a drug delivery system. Then in biotechnology, we have the strain, so selection of strains, engineering of strains. We have also possibility to fine-tune the polymers during bioprocesses. So there is also a big need of engineers that can actually produce the material and also scaling up the production. And then last but not least, the application or processing, maybe before compounding, fine-tuning the material properties. So that's an important part. So for everybody, there is plenty of work to be done.
We've been speaking to Manfred Zinn, professor at the Institute of Life Sciences at the University of Applied Sciences and Arts in Sion, Switzerland.
Dana, was there anything in particular that stood out to you from this conversation?
Yeah, just the sheer amount of plastics that we produce every year. I think Manfred said it was 450 million tons.
And the volume of that of course doesn't get recycled or doesn't get properly disposed of is really concerning. And then the knock-on effects that has with the microplastics that are entering our environments and bodies as well.
Yeah, I think we also discussed some pretty staggering statistics that really offer us a reality check of the current situation.
And at the same time, I'm also hearing that there's real potential for changing things as well. And so I think the importance of this research and also some of the really interesting, when he's talking about 3D printing and some really significant changes in how we even go about the industrial process around this material, I think we're just at the beginning of where this could take us.
This has been Balancing the Future from METTLER Toledo.
What questions about science and technology do you want answered in a future episode?
Let us know by leaving a review, or if you're a Spotify user, leave us a message in the comments section.
And be sure to subscribe wherever you get your podcasts.
We'll be back in 2 weeks with our next episode. See you then.